Before I say anything about how we actually adjust the weights on our neural networks, I do want to talk about something I was said in or did in the last video, which is I had called our activation function F, completely forgetting the fact that we already had a function F that was the feature. So here I have the activation function, and here I had the feature generating function. Right? Obviously, we can't let that stand. We have to have deconflict. So since activation function starts with A, what we will do for going forward is call call this function A of X. Okay, recall that our Y sub K, I think I was using, is equal to now A of the sum. I'm going to use the summation notation, J W J K times A of the sum of all across all I of W I J times our input X of I. All right, now what are we going to do with this? Well, we're going to take this and we're going to define ourselves an error function. We'll call E. And E is going to be defined as 1/2 the sum across all K of Y star K minus Y K squared. So why do we do that? Well, so the 1/2 will just be a mystery for a minute or two, so we'll talk about that later. Here we've got if we have a bunch of different outputs, several output nodes, which is allowed now, we sum across all of them, and then we look at what our desired output was minus our actual output. And then we square it. So why do we square it? Well, there are two things we want our error function to be. One is we want it to be always positive, right? We want it to be an absolute measure of the error. So this squaring this actually does that. It makes sure it's positive. But why not something else? I mean, we could have said our error was equal to 1/2 the sum across all K, the absolute value of YK star minus YK, like that. The reason we don't do that is because the absolute value, although it is always positive everywhere, it's not continuously differentiable. There's a point in the middle of this where there is no derivative. And as we'll see in a minute or two, we actually want to have this be to be able to take the derivative of our function everywhere. All right. So we've got our error function then, and our goal is going to be to minimize this thing, right? So how do we do that? Well, if you remember from your calculus that you all took plebe year, right, we can minimize functions by taking the derivative, and then there's several different techniques. One would be to take the derivative and solve for the zeros. As we'll see, that's not going to work out very well because the derivative of this thing is going to be super ugly, and we're not going to know how to solve for it. Another is Newton's method, which also doesn't work particularly well for this problem. But a Another method is known as gradient descent. And in gradient descent, what we do is we take the derivative of our error function, and then with respect to the weights, and then what we do is we move our weights to in the direction of the gradient in order to reduce the output of this function and thus minimizing it. Gradient descent is not guaranteed to find the minimum, but if you do a bunch of random restarts, you can often find a global minimum, or at least a good approximation of a global minimum from this in general. All right, so let's expand out our error function here. It's 1/2 the sum across all k of y star k. Remember, y star is what we actually want, our target function, or target vector. And then let's expand this out. This is a of j w j k times a of the sum across all I w I j times x sub I. Whew. This is pretty ugly, so let's create a couple of things to simplify this out for us. Let's just let n sub k equal this inner part here. So that is sum of all j across all j, w j k times the activation function I w I j x sub I. All right, so that will be one handy thing. And let's also let m sub j be equal to this inner piece. So we can say the sum across all I of w I j x sub I. All right, in this case, the error function then becomes 1/2 sum of all k y star k minus activation function n k. And we'll just leave it like that for now, and we'll only expand out n sub k when we need to as we're taking the derivative. Oh, and of course, this is squared. So now, in order to perform our gradient descent, we actually have to find the gradient at some point. And so we actually need to take the derivative of the error function. And what are we going to take it with respect to? Well, we're going to take it with respect to the weights. Now, the question is, which weights? Right? In fact, actually, we have two sets of weights. So which weights are we taking the derivative for? Well, if we look at these weights perform, each set of weights works pretty much the same within the set, but they do have very different properties between the two different sets. So we're going to treat each set of weights differently. And we're going to start off with talking about what we call the outer weights, the weights that are closest to the output. And I'm going to do this in terms of some arbitrary weight I'll call WBC that's inside the set of WJK weights. And then we can apply this rule to each of those weights individually. It's good to note that there is a more concise way to write all of this, and get rid of the summations using just vector notation. But unless you're familiar with linear algebra, that can get a little bit confusing, so we're going to stick with the more verbose method. So this is equal to the derivative BC of 1/2. Well, 1/2 what? Well, I almost copied the summation down, but in fact, BC is an output weight. So only one of the K output weights is actually connected to BC. So in fact, we can eliminate all of the other sums, all the other terms in the sum, because they are not they don't contain weight BC. So that means we can just make this 1/2 y star c, just that one. Here, that's not a great C. Y star C minus the activation function. And the same thing is true for n. We're not interested in all of the n's, only the n that is connected to, that is involved with this weight, that feeds into this weight. And so that's n sub c squared. Next, we know by the chain rule that when we have some function, some composite function, we're taking the derivative of the outer piece, just focusing on this power here, at times the derivative then separately of the inner piece. So what does that look like? This is 2 times 1/2. Now suddenly maybe it becomes clear why this 1/2 was here, just to get rid of that 2, so that simplifies away, times y star c minus a of nc times the derivative of the interior, which was y star c minus a of n sub c. Next, when we take the derivative of this internal portion here, this is just a constant that we've been given by as part of our training data. So that, with the derivative of that, just goes to 0. So this becomes a negative, and the derivative of this. And so we're going to move this negative back outside. So this equals opposite of y star sub c minus a of n sub c times the derivative of n sub c, which we know is, all down again, right? We take the chain rule again. This becomes a derivative of a n sub c. Remember, we know this fact because that was one of the reasons we picked the logistic function in particular, so that we could do this. And that is times the derivative of this n sub c. Okay, so now it's time to break this out and say, okay, for any particular k, n sub k is this thing, but we're going to leave this thing in terms of m, so that we don't have to make that quite so complicated. And that becomes of sum across all j of w. Now we don't need all of these, we just need those weights that feed in to C, those right, that affect this. So we can make that W J C F of M sub J. So I just want to make an aside here and talk a little bit about all of these elements of the summation that we're getting rid of. So remember, we're trying to find the derivative with respect to some WBC here. This is the single weight. And so I eliminated a lot of other weights when taking the derivative. And why was that? Well, because look at here's another weight, but this weight has no effect on the value that comes out of this. And this weight has no effect on the value that comes out of here. And similarly, this weight does affect, this weight affects, and this weight affects, but these weights all have nothing to do with that, with this WBC. So that's the picture, that's the sort of the visual picture of what's going on there. So here we are with the summation removed and just our final derivative to take. So we're taking the derivative with respect to W sub BC, and we have WBC right there. Notice this activation function times M sub B is the hidden layer, and so that doesn't have any WBCs in it since we're doing the derivative with respect to the outer layer. And so this is just a constant, and so the derivative of this just becomes A of M sub B, and then copy that down. We get that. So this gives us the learning rule that says we take WBC weight and we want to update it by taking WBC and then moving. So now we want to add in some alpha, which is a learning rate, just like in other applications, of our y star c minus a of n sub c times a prime of n sub c times a of m sub b. So two things to note here. What happened to this negative sign? Well, what we're trying to do is move in the direction, trying to move in the opposite of the direction of the gradient. So instead of moving up to make the value of the function higher, we're trying to move down. So we move in the opposite direction. So we subtract this, and by subtracting this with the negative, that becomes a plus. The alpha is a learning rate, so we make small hops so we don't overshoot where we need to go. And then notice this interesting thing about this is that this looks a lot like the perceptron learning rule. We've got basically the error term right there, and we've got an input element right there, and the only thing that's different is now we've got that thing with the derivative right there. So this is the update just for all of the WBCs, which are the outer layer weights. Now we have to move on to the inner layer weights. Now we're going to have to start all over in order to find our derivative gradient of the error function with respect to some weight WAB, where WAB is a weight in the hidden layer, that is one farther back. All right, so we know that this is equal to just plugging in the error function here. Is y stars k minus a of n sub k squared. So we've already done the first part of this, so we know what this is going to be. We're going to have this negative sign up here. Actually, we have to leave that summation k across k in there, because in fact, now that we're taking derivative with respect to AB, these hidden layer weights, all of that's going to end up feeding into all of the weights in the outer layer, so we can't remove some of those. So that's going to make this a bit more complex, but we can still sum across all k of y star k minus a of n sub k times a prime of n sub k times the derivative w a b of n sub k. We can, here, I'll move this over a little bit. We can expand this out and ignore any of the terms that don't actually contain WAB. We get WBK times A of the sum across all I of WIB times X sub I. We apply the chain rule again, and we get WBK A prime of MB times the derivative WAB of MB, which is WIBXI. In here, there's only one weight that actually is related to, contains, or one term that contains WAB, and that's the one with WAB in it, so we can simplify this to of WABXI which gives us sum across all k, y star k minus a of n sub k times a prime of n sub k times WBK times a prime of m sub b times x sub I. So, yeah, that's a little bit more complex than what we had before, but we still have the basic parts. Now we're going to sum across a bunch of things because this weight is this weight is affecting a lot of different, several different outputs, whereas the WBC was only affecting one output directly. So that's still there. But we still have the error term, we still have the derivative, the weight term, the input term, and now we've got the two derivatives of our activation function. And so that seems like a fairly reasonable thing, and so we put that directly into an update rule as thus. And we still have the same elements. We've got because we're moving the opposite, we're going to subtract, and so the subtraction then of the negative becomes a positive. We've got our alpha less than 1 learning rate to keep us from jumping too far, and then we've got the actual derivative with respect to a, b there. So that was a little long, so I will wrap up and have some final thoughts in a separate video.